I don't want to give you one more thing to worry about or keep you up at night, but here's one. Okay, where's all this carbon dioxide end up that we're kicking up? You're worried about greenhouse effect and all these things. Well, I'm not saying it's real or not, even though pretty much every climatologist in the world says it's real. They know a lot of this carbon dioxide that we've been kicking out goes into the ocean. It just hasn't dissolved all the CO2 it can, so a lot of it ends up there. And they say like we kick out about 8 gigatons of carbon in the air, and about a fourth of it goes into the ocean. But what keeps up, I think, from my perspective, from what I've read, what keeps up these guys at night is if the climate keeps climbing up in temperature just a little bit, it's going to affect the solubility of what's already been in the ocean. We've been putting out a lot of stuff and dissolving in the ocean ever since the Industrial Revolution. And if it can't hold much more, instead of absorbing, it starts kicking it out. I mean, it's going to be more than an exponential increase in CO2 in the atmosphere. So it's a real concern, and they don't know. But so just la-la-dee-da. Okay. So solubility, that's what the whole idea was with the CO2 in the ocean, except as a gas dissolved. But there's also some other solubility equilibrium going on there. But writing solubility product KSP expressions, or chemical reactions. Danielle, in the question, what is the solubility of calcium sulfate? What is meant by solubility? Yeah. How much of what dissolves in the water? How much of the CaSO4? How much of that calcium sulfate dissolves in the water? Exactly. Right? You can like how many moles per liter, how many grams per milliliter, how many, right? Just the amount. It's concentration, I guess, right? What it would be. And it is. It's true. It's always water. That's what we're interested in. We're walking bags of water. Water is the most common solvent. Water's in our environment. Water's where it's at, and water's what it could be anything, but we're going to stick with water. Do you have to have a saturated solution to measure solubility? Miranda, do you have to have what is a saturated solution? Saturated. What does that mean? Anybody know? The amount of solute has exceeded the amount it can hold. Well, it hasn't quite exceeded it. It met it. It met it. It can't hold any more.
Isn't that
right?
super saturated?
Super saturated is when it went over. Went over. Then you shake the system and it all comes out. Yeah. So saturated. So that's what saturated is. It can't hold any more. Do you have to have a saturated solution to measure solubility? Right? Because you could put in just a little bit, have it dissolve. Even though you could put in some more and have it dissolve, but you quit. Do you have to have a saturated solution to measure solubility? Because if you think of it this way, if you haven't met the limit, right, you keep on adding a little bit more, a little bit more, a little bit more. Well, then your amount that Danielle said, the amount that you dissolve per liter, per milliliter, it keeps going up. Well, solubility can't go up. It has to be some fixed number. So it only makes sense if you have a saturated solution. That's the only time you can talk about solubility. There has to be that dynamic equilibrium going between the solid, like here, the solid entering the solution, and the solution going back and precipitating out. That rate of forward and reverse reaction has to be the same. That dynamic equilibrium, those rates of dissolving, the rates of precipitating have to be the same. You can't stop it, but the rates are the same, so the concentrations aren't changing. Okay. So you have to have a saturated solution. We introduced solubility rules in Gen Chem, general chemistry. Miriam, what was that? Solubility rules. What were they? Remember? You want to remember? What were they good for?
The first group of periodic tables and all of those dissolve.
Okay, there's one of the, what Nyla just said is probably the biggest rule in the solubility rules. Group 1, anything with the group 1 metal always, always, always dissolves. It's always soluble. So solubility rules are just a whole bunch of rules like that, right? And they got really specific. They said, oh, sulfate will be soluble unless it's with, I don't even remember, because I just, you need it, you Google it, you look it up. But the one rule that I have just burned in my head is that first one, what Nyla just said. Any metal, right, lithium, sodium, potassium, you see that, it's always going to dissolve, 100%. Okay. So that's kind of what they were. We used them to see what did or what didn't dissolve in water really, really well. Okay. But the stuff that we're going to be talking about, it may, there's this whole range of solubility. Some things dissolve really well, some things don't, like a rainbow effect. And that's kind of where we're coming from. We're going to mess with all these compounds. The solubility product constant. Oh, the solubility product constant. The equilibrium constant for solubility reactions. And a solubility reaction, the reason why they call that a solubility reaction is you have to have, all right, it has to be saturated. You have to have a dynamic equilibrium going on with the solid. And you write this reaction, and you have products over reactants, and you write the equilibrium constant for it. Can't be changing over time. It's just a constant, products over reactants. What's the symbol for it? Adriana? KSP. Yep. And whenever you have an equilibrium constant with a little subscript, that means that, man, these things are tabulated. They're all over the place. You can just look them up. You can Google them. But they only make sense if you write the reaction the right way. There's a convention. And we have to know how to write that reaction. You got to know the convention. Kathleen, what's the convention? Yeah? The concentrations, the ions, it's this dynamic equilibrium. Wow, we should have a backwards arrow. What side do we put these ions on? Yeah, on the right side. The solid goes to its ions. You always write the solid on that side, the ions over there. Make sure it's balanced and everything. But the point is the pure solid has to be over here. Okay, that's the convention. It doesn't have to be. I mean, if it's over on the product side, fine, but you better stick to it. But all the tables are using that convention, so we're stuck with it. You got to write the solid on the reactant side. Okay, so then they start talking about solubility, right? And Danielle kind of gave us an idea of what it was. But Casey, how do you calculate it? How do you calculate it? Anyone remember? We're going to do products over reactants. How do we do it? Yeah, you're right. We're going to be setting up this KSP thing, and we'll have products over reactant. Well, the reactant is always going to be what? 1. So we'll have the products over there. And we're going to use this, you're right, but that doesn't give us solubility. It has to be some number, right? Like Danielle said, oh, it's grams per liter, milliliters, moles per liter. It has to have some concentration to it. How did we get that number? We did. Oh, we'll use the tables to get the KSP. Good. We'll get the tables to get the KSP number, or they'll give it to us. We'll need that. And then here we have these concentrations. We did. Here, I'll give you, see if you recognize this.
Oh, ice.
We did ice. We did ice. This is what you got to remember now. Solubility is the what? X in ice. That's all you really got to remember. Solubility is the X in ice. And ice is always for a reaction. It's got to be for the KSP reaction. Otherwise, the little X doesn't make sense.
That's
That's how you're going to find solubility every single time. We're going to find X in ice. Yeah, I remember. Okay, we're going to do them, but let's just give you the full story first, right? So if you do ice, what did we do down the solid all the way down? Dashes. I like dashes, right? Zeros could screw you up. And then usually, almost always, we would put dashes in the ions for the initial row. Why? Yes, yeah, it's what you start with. There's nothing there, right? They don't say anything. They just say, what's the solubility of calcium sulfate? They didn't say anything, so you just put dashes in the initial row, right? But what, because you have all these ions there. But what if they would have said, what's the solubility of calcium sulfate in 0.1 molar sodium sulfate? Right? Now it's not pure water anymore. You have something there initially. Right? So you'd put under the sulfate ion, you'd put what concentration? 0.1. Right. What if, let's see. Well, okay. We'll play with that. That's where we're headed. So we're going to fill out the ice table and solve for X. Oh, here's a demonstration of it. Okay. What is the solubility of calcium hydroxide? Here it is. Right? And we want to find its solubility. Before we work it out, Nyla, we're actually going to, I think we could titrate this. We could, well, if we set up the ice table, we'll see that our solubility is really related to our hydroxide concentration. We'll see that. But the point is, we could do a titration of this stuff and get the concentration of hydroxide, get our solubility. Just trust me on that. So we have to pipette, right, some of this out of there. What if this solid wasn't there? Could we still pipette that solution? Right? So in other words, we pour it off, and then we give it to Kimberly or something, and then she pipettes out. Does that solid have to be there is what I'm trying to get at?
I think so, because whatever is dissolved is already in the top.
Right. It's just that if you give it, she's right, it's not necessary. The point is though, by having that solid in there, Kimberly knows that it's a saturated solution. But so you'd have to tell her, Kimberly, this is a saturated solution. Right? Otherwise she wouldn't know, because there's no solid in there. Make sense? Okay, so let's solve this. Okay, so first we have to find X in ice. We have to write the KSP reaction. So Pablo, what would we write for a KSP reaction? What has to be on the reactant side? Well, on the reactant side has to be the solid.
Is it always going to be a solid?
What's the convention? You have to do it that way. Okay. And then the product, Amanda, the ions, you'd write what? Calcium. And the OH. Now, what's the charge on the calcium? Does everyone see it? Yeah, the little hint is there. Or it's in group 2. Either one works for you. And it's 2 OHs. Exactly. Okay. Now we have to do ice. Down the solid, let's just put, right? Otherwise, you might stick an X in there or something, right? So that's the first thing I do.
What does I stand for again?
Initial. I is initial. C is, that's a good one. C is change. E is at equilibrium. Here's where all your answers are, in the E row. Right? That's where all your answers are. Okay. So initial, change, equilibrium. Good. Thanks for asking that. Okay. So is there anything there initially? Is there anything to put in the initial row? No. But let's just cover all of our bases. Pedro, make something up. Now we're not gonna change the question, but make something up so that we would have to put something in the initial row. It's in so all this doesn't change. Blah 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 blah. In what? In 0.01 molar. What could it be? Then we have to put something in the initial row. What could it be? Exactly. Yeah, he's getting there. It has to be something with calcium, or it has to be something with hydroxide. So make something up. 0.01 molar calcium. Oh, not calcium hydroxide. That's what we have. Okay, now calcium phosphate. Okay, now it's. See, he went the hard route. The reason why he went the hard route is because you got to know your solubility rules to make up this question. Is calcium phosphate a precipitate? I don't know. So, but I do know one anion. If you remember these solubility rules, if you can answer this question, you're doing really good. What is there's two anions. What are the two anions? You put these anions with anything, any metal, it will always, 100%, totally dissolve. Not carbonate, not chloride, not salt. Nitrate's one of them. Woo-hoo-hoo! Nitrate and acetate. So to finish Pedro's question, you'd have to use nitrate or something. Okay. I thought he was going to say like sodium hydroxide or lithium hydroxide or something like that. All right? Because I know that's the one rule that I remember really, really well. Okay. So if that's the case, you'd have to put the 0.0. What would you do? Would you put 0.01 here? Or oh no, it's calcium. You'd put 0.01 here, right? What if it was 0.01 molar sodium hydroxide? Would you put 0.01 here or 0.02? Because there's a 2 there. I'm being a jerk. 0.01. 0.01. Because that's the initial concentration. So you just put the initial concentration there. Doesn't matter what that coefficient is. Okay. Okay. Okay, so now we have to, there's nothing there initially, dashes. Okay, change row. What did we put in the change row, John? Yeah, it's the x's. Okay, is it minus x or plus x? The arrow's going this way. This stuff is forming. This stuff is reacting. So if you ever had x's over here, they'd be minus. Ever have them over here, they're plus. So it's plus x and 2x. How do we always get the equilibrium row? Yeah?
We're putting x because that's what we're going to
That's the change. That's an x. X is what we're going to be solving for. Because solubility is the x in ice. That's what we're after. And you could use y's or whatever, but we always use x's, so fine. How did you get the equilibrium row? All of our answers. These are the concentrations at equilibrium. You just add them up. So we have nothing plus x. You just get x. You have nothing plus 2x. You just have 2x. Okay? So now our KSP was what? 5 times 10 to the negative 6. And I strongly suggest not just doing the x things right away, because you're going to, odds are you might make a silly mistake. Unless you've done this a gazillion times. I would write this first. Why? Why am I suggesting this? So you don't forget the power. You see what I'm heading at, right? Otherwise, you might have just wrote x and 2x in there. You might forget that. So I would write that, and then it's straightforward. This is 5 times 10 to the negative 6. Has to equal the equilibrium concentration of calcium times the equilibrium concentration of hydroxide squared. You multiply those guys together, you should get this number if you're at equilibrium. Well, we are at equilibrium. So here's my concentration of calcium. There's my concentration of hydroxide. So you just put them in. So I've got X and 2X, but I have to square it because the hydroxide is squared. So I've got 4X to the third cubed. Solve for X. So divide it by 4, then what? Raise both sides to the 1/3 power, or take the cube root, whichever your calculator can handle. Right? My $6 job, you can do either one. It's light though. Sorry. Yours doesn't need light. Divide it by 4. Cube root. I got about 0.011. Somewhere around there. Make sure you can get that. Okay. Now, what do you put as units? What do you put as units? Right? Because this is X. It needs to be a concentration. Big M. Big M. What's really common, I don't know why they do this. What is the solubility in, does anyone remember? What are the units they really like for solubility? I don't know why. Must be some history thing. Grams per liter. I don't know why. They always, a lot of times they ask for that. Yeah, but the homework will too. You have to convert this to grams per liter. How would you do that? If it asked you. We have 0.011. What are the units? Big M is, what is it? Moles per liter. Moles of solid or liter of solution. Oh, it looks like we just need to do what? Molar mass. You have a mole. I don't know. What's a calcium, 2 oxygens, and a hydrogen? Calcium is about 40.1. And a hydrogen's 1.01. Oh, I need 2 of them, though. And then 2 oxygens is about 32. About 74.12 grams. See, then I'll have grams per liter. That's the other way. So the 74.12 times 0.011. About 0.8. 0.8 grams per liter is how much of that stuff would dissolve in a liter. Okay. Make sense? That's the game you're playing. Which will be more soluble? Which will be more soluble? Barium iodate or calcium iodate? How would you answer this question? Again, what's solubility? It's the... No. It's the X in ice. So when you see solubility or what's more soluble, always think X in ice. That's what you got to do every single time. So you could set this up. Now, before you start writing, you could set this up. Write up the barium iodate, KSP reaction, X in ice. Calcium iodate, X in ice. Do you notice anything similar? Can you see it without writing it? Would there be something similar in there? There's no initial, that's true. What else is similar? Yeah, the ions. will have the same, what's the word? Stoichiometric coefficients. You're going to have the exact same format. I mean, you can write this out, but you're going to have the exact same ice table for both ones. You're going to have, I don't know, whether you're dividing by 4, taking the square root or cube root, you're going to be doing it the same both times. So can't we just look at the KSPs? Right? If we just look at the KSPs. Now, if you're not comfortable doing this, you should work it out. All I'm saying is you might end up with, well, you would. You would end up with, on both of these, KSP equals, let's see, it's going to be x times 2x squared. This is what you're going to end up with for both of them. If you did all the work, right? Do all the work. You're going to get KSP equals x times 2x squared. Now, I've done this a gazillion times. All I'm saying is you look at these, because they might give you even more. If you look at these, if these are in the same format, the same stoichiometric coefficients when you break these up, they don't even have to be I-dates. They could have been different. The point is that you have, stoichiometric coefficient of 1, stoichiometric coefficient 2. They don't have to. One could have been a chloride. Doesn't matter. As long as the KSP format's the same, the algebra is the same. You're right. We're after our x, and then whichever x is smaller, he's going to have a lower solubility. But you can just look at the KSP. A smaller KSP is going to be a smaller x. A bigger KSP would be a bigger x. So you have 10 to the negative 7. You have 10 to the negative 9. Which number's bigger? 10 to the negative 7. This is a bigger number. So he will be more soluble. The bigger the KSP, the more soluble. If they match. Let's make one where it wouldn't match. Let's say you have calcium chloride and what would be another one? How about magnesium sulfate? They don't match, right? If they match stoichiometrically, there must be a better word. Ratio-wise, coefficient-wise, if they match that way. These don't. You don't have any choice unless your brain's a lot better than mine. I'd have to find x and ice for both of those and solve for it. Right? I would have to do that if it was those two. But if they're in the same format, you can just look at the KSPs. Okay, find the concentration of copper in equilibrium with copper bromide solid. Is this a KSP, a solubility problem? They didn't even mention solubility. Yeah, it means it. It is a solubility problem. You're going to have to find the KSP from the table, look it up, and if you can envision the ice table, that x is immediately under this. So your solubility is the concentration of the copper 1. All right? Write it out. Write out the KSP reaction, the solid going to its ions. It only takes 5 seconds. Write that out. Write out the ice table. Fill it in. And you're going to see x is the copper 1 concentration. So really you are after solubility. It is a solubility problem. Oh yeah, what are our tables here? You guys don't have a book. Well, someone had their phone on. They can Google this. It takes forever to find this stuff, doesn't it? Standard reduction potentials. Oh, here's a whole bunch. It starts on page AP9. AP9. We're supposed to be looking for copper bromide. AP9 is where it starts, so you can do your homework. There it is. AP9, you look under bromides. It's kind of an odd way of doing this. Look on page AP9. And then they have this table where they have Cu, where L equals Br minus. Then they have a CuL. That's, I don't know, it's kind of weird how they do it. If you're going to type L, why not just type bromine everywhere? That's how they did it. So you find it. My little L are the bromides. Go down and find it's where it's copper. And it's 5 times 10 to the negative 9. KSP. Okay. Oh, hold it. I'm supposed to be up here. So the solid goes to its ions. Hopefully you have this. Ice. Dashes. Dashes. X's. Right. So we'll end up with 5 times 10 to the negative 9 has to equal x squared. And look at that E row for your answers. E row is the equilibrium row. If they want to know the concentration of anything, you just look in here. And copper 1 is X. So you find your X, and that's your answer. That makes sense? What if I would have modified this somehow? Just pretend this was a 3 for whatever reason. That makes this a 3. That makes this a 3, right? Everybody with me? Now what would be the concentration of your copper 1? 3. What is it? 3x. Just 3x. Because you look in the E row for your answers. It'd just be 3x. That'd be the concentration of your copper. But there's no 3's. Okay. This other question. So what changes in the ice table? The initial. Exactly. You have to put a 0.1 under the BR. Remember these guys? Pretend they're not even there. Right? Those group 1s, they're always spectator ions. It's just there so you can get the bromide in solution. So now you have a 0.1 under the bromide. Exact same problem. So our 5 times 10 to the negative 9 x times 1 plus x. Oh. What do we do on stuff like this?
5 or higher, you could ignore the quadratic formula.
Right. Okay. Do you hear what Pablo's saying? If it's 5 or higher, what is he talking about? Yeah. So, or higher. So what's 6, 7, 8, 9? Is that number getting smaller or bigger? Smaller, because it's 10 to the negative 6, 10 to the negative 7, 10 to the negative 8, 10 to the negative. So this is going to be a really, really small number. Well, that really small number has to equal x times. That means x has to be really, really small. So what Pablo's saying is if this is negative 5 or worse, negative 6, 7, 8, 9, x has got to be really, really small. So if you have somewhat of a big number here plus your x, this is pretty much going to be 0.1 plus 0.00006 or something. Wow, that's going to be really 0.1. So you can just say, oh, this is approximately x times 0.1. If you're not comfortable with it, just do the quadratic equation. You can always do that. Or you could also solve for your x and see if it is a lot smaller than 0.1. If it's not a lot smaller than 0.1, then you better go back and do the quadratic. Okay. Because negative 5 is really cutting it kind of close. Negative 9, no worries. But when you get down to negative 5, usually you can get by with it. You can, but right? Because you're just you're approximating. You're not going to get the exact answer for x, but it's really, really close.
So if it's bigger than 10.8, if I discard it,
Yeah. -5 or -5, -6, -7. Yeah, it almost always works. What's the sig fig problem? I wouldn't discard it. Okay. So what's our answer? It would be 5 times 10 to the -8, right? Divide both sides by 0.1. Make sense? Because look at that. That's 0.1, 2, 3, 4, 5, 6, 7, and a 5. Compare that to 0.1. You get 0.1. That's all Pablo's saying. It works. Okay. Find the concentration of copper in a solution saturated with whatever the heck that thing is if the hydroxide is fixed at 1 times 10 to the -6 molar. Note that that whole big complex gives 1 mole of sulfate for every 4 moles of copper. I guess there's just a KSP reaction. Yeah, it's true. 4 moles of copper for every 1 mole of sulfate. Kind of redundant. Why even say that? That's okay, I guess. They want you to find the concentration of copper. How would you start? It's KSP. Ice. I mean, what other way do you have? Because, oh, what's the concentration of this guy? What's the concentration of that guy? You pretty much have to make an ice table, look in the E row for your answers, because there they are. That's the only way we have to attack this, is to make an ice table. We have no choice. That's the only weapon you have. This, right there, that row. It's your answers. It's your answers for copper. It's your answer for hydroxide. It's your answer for sulfate. It's your only choice. Okay, so E. This is a solid, so no problems there. Initial. Is there anything there initially? Oh yeah, that hydroxide is 1 times 10 to the -6, right? It's fixed at it. It's fixed at 1 times 10 to the -6. So how would you write that? It's fixed. That means it doesn't change. I don't know. Wait, 1 times 10 to the -6. I'm just trying to say this guy is always 1 times 10 to the -6. Because there is no change. He's fixed at 1 times 10 to the -6. No. Well, it doesn't. Well, I think it'll make more sense. Let me show you this. This is what I'm getting at. I did that because I want to make sure I do this right. This is what I was worried about myself screwing up. The KSP is what number? 2.3 times 10 to the -69. Holy cow. Okay. Now that has to equal. Okay, now what would you say it's going to equal? How would you write the expression? Cu plus 2, it's in brackets, raised to what power? To the 4th. Keep going. Times OH to what power? The 6. And then sulfate to the 1st. Okay. So what what'd I do? All right. Hydroxide to the 6. What I was worried that I was going to do is this concentration of hydroxide has to be what? That concentration is fixed at, yeah, thanks. There it is. Yeah, it's fixed at that. That's what I was worried I was going to screw up.
It's also raised to the 6th power?
Yeah, because it's the concentration of hydroxide to the 6th power.
Okay.
So it's going to be 1 times 10 negative 6 to the 6th power. So we can put that in right away. We'll have this guy to the 4th. We'll have 1 times 10 to the negative 6 to the 6th. And then we'll have that guy. Right? So we don't know what the copper and the sulfate are. We'll have to get that from our ice table. And that's why I was kind of, I don't know how else to do it. This guy right here is fixed at 1 times 10 to the negative 6. There is no x.
The attitude is fixed, right?
He's fixed. He said it was. The question said it was. Okay, so is there anything initially there for the copper? No. The sulfate? If there was, we'd put it in. The change for copper, you'd put 4x. The change for sulfate, x. Add stuff up, 4x and x. So 4x for the concentration, 'cause that is the concentration of copper at equilibrium. X is the concentration of sulfate at equilibrium. 4x to the 4th, and you have an x over there. The whole question, what did I want? I forget. Find this guy. Find the concentration of copper. So when you finally do get your answer, when you finally do get your x, you do a whole bunch of stuff. Right? You finally get your x, such a big M. How do you get your final answer? Multiply it by 4. Because they want to know the concentration of that copper too. And that is right here. All your answers are in the E row. It's going to be 4x. Multiply it by 4. Exactly. So see if you can get it. Well, we're about out of time, but 2.3 times 10 to the negative 69. Divide it by 1 times 10 to the negative 6 to the 6. Divided that by, right? Ew. Let's use calculators better here. Go. And then the 5th root. Done. I don't know if it's right or not, though. Did anybody get an answer? I got 9.8 times. No, mine's right. Because what I did is I put this number in for x, and I got that. So that's right. So what I... Hold it. Yeah. Yeah, I had to take this divided by 4 to the 4th. Then I hit divided by this to the 6th. And I got equals. Then I took the 5th root, which is raising everything to the 0.2. Right? That's something else that helps me. If I know that x to the 5th equals, I don't care, 76, that means, well, do you remember this? If x squared is 9, x is 3, because you just take the square root of both sides. But that's the same as raising everything to the 1/2. You just flip it. So x to the 5th to the 1/5. And then I'd have my x. So come by. I'll be glad to help you out with this.